G'day everyone, Week 8 summary. Today we're looking at indices primarily and doing a few questions and a bit of algebra with them. So first thing we're going to look at is index laws, and starting off we've just got, say, I'll move off straight lines, say we've got something like 2 to the 3. Well, first, terminology, we call this the base. And we call this the exponent, or the index, or we can also call it the power. And 2 to the 3, what does that equal? Well, it's the same as saying 2 times 2 times 2. It's 2 3 times, which is the same as 8. So the exponent just gives us how many times we have the number multiplied by itself. Okay, so that's pretty basic. So next thing is to have a look at some of the laws that govern indices. Number 2. Wow, what just happened there? Number 2 is index laws. Done it again. Okay, number 2, index laws. So the basics. A to the 1 equals, well, let's look at an example. 2 to the power of 1 equals 2. You can put that in the calculator. Just equals A. A to the power of 0. You'll find if you pop it into calculator, it equals 1. What about a to the power of negative 1? To the power of negative 1 equals the same as 1 over 2 to the power of 1, which in this case is 1 over 2. Probably better to express that with n. And then we've got the kind of combination ones. A to the n to the power of m equals a to the n times m. A to the n times a to the m equals a to the n plus m. So an example of this one could be, this top one could be 2 to the power of 2 to the power of 3. Well, if we write that out, it would be 2 times 2 times 2 times 2 times 2 times 2, which equals 4 times 4, 16, times 4 is 64, 64, which is the same as saying 2 to the power of 6. 2 times 2 times 2 times 2 times 2. So hopefully that's clear enough. And then these ones, 2 squared times 2 cubed equals, well, this is 2 times 2 is 4, times 2 times 2 times 2 is 8, equals 4 times 8, well, 2 times 8 is 16, and one more times 2 is 32. So, which is the same as 2 to the power of 5, which is just our 2 plus our 3. So here we see that a to the m times a to the m equals a to the n plus m. And a to the n divided by a to the m equals a to the n minus m. So there are basic laws. Perhaps we should look at a bit of an example. What if we want to simplify to see these laws in action? A squared over b cubed, or times b cubed, so the negative 2 over a to the 7 and b to the negative 8. So what's the first thing we can do? Well, first thing is I would suggest we could use a to the n m equals a to the n times m. So that gives us a 2 times negative 2 and b 3 times negative 2 over our bottom, which is a to the negative 4, just a b to the negative 6 over a 7 a to the negative 8. Now, I keep on writing a, b. And so when we're looking at this, we can realize that this is exactly the same as a to the negative 4 over a to the 7. You don't have to write this out, but I'm just writing this out for clarification. Now we can use the law a to the m divided by a to the n equals a to the m minus n. And so we go from here, this becomes a to the negative 4 minus 7 times b to the negative 6 minus negative 8 equals a to the negative 11 b to the negative 6 plus 8 equals a to the negative 11 b squared. And so that's our simplified version. And so that's how we can use some of these index laws. We use this one, we use this one to do a simplification. Okay, just wondering if we had any more examples to look at there. No, I think that's pretty good. Now 3, algebraic fractions. So algebraic fractions essentially combines a process, or it's a combined process of thinking about fractions and also thinking about indices. And a key thing to remember here, man, I keep on doing that. A key thing to remember here is that the laws for indices, the laws for pronumerals, our A's and our B's and our C's and our D's, etc., are exactly the same as our laws for numbers. So the laws, the index laws here that we use for A are exactly the same as the index laws when we apply them to an actual number. So this is 3. So I might write that down. So laws for numbers are same as laws for pronumerals. So let's think of an example here. Say we want to simplify this equation or this expression because there's no equal signs. 10a squared minus 5a divided by 9a over 8a minus 4. So by now when you see one fraction divided by another fraction, the first thing you should be saying is flip. Flip that one. So we end up with 2 over 10a squared minus 5a times 8a minus 4 over 9a. There's a couple of different ways to do this, but I'm going to go ahead and say, usually in a case like this, you'd say top times top and bottom times bottom. And so we end up with 2 outside of 8a minus 4 and 9a outside of 10a squared minus 5a. Okay, so this is what we're looking at. We were looking at this question in tutorial today, and this was kind of a point at which quite a few people found it a bit tricky. So I'm going to do a bit of an aside here and talk about exactly what we're doing when we're cancelling in fractions. So by now, if I write out a fraction something like 8 on 4, right? 4 on 8. If I write 4 on 8, I think probably quite quickly you would be able to say that, well, that equals 1 on 2. But let's have a bit of a deeper look at what we're actually doing here. 4 on 8, what we're doing here is we're saying, well, if we divide 4 divided by 4, we end up with 1. And if we have 8 divided by 4, we end up with 2. So what we can actually write this as is we take 4 out of the top, and we have 1. And we take 4 out of the bottom, and we have 2. Right? And then we can cancel those 4s, and we end up with, therefore, 4 on 8 equals 1 on 2. So this is what we've done. We've said, okay, we've got a fraction. We want to simplify it. What can we take out of top and bottom? What can we take out of top and bottom? Man. Top and bottom to then cancel, or LE, depending on where you come from. So we can ask this question now. We asked the question here, what can we take out of top and bottom? The answer was 4. But what about here? What can we take out of top and bottom? Well, can we take 2 out of top and bottom? Well, we can't take the 2 out of this 5, and the 5 when we multiply it by the 9, well, that's not going to be very helpful anyway. So what we'll first take out of here is, out of the top, is we'll take 2 out of here. So we end up with 4 outside of 4a minus, hold on, minus, actually we'll take 4 out of this. So this becomes 8 outside of 2a minus 1, because 8a divided by 4 is 8a divided by 4 is 2a. Negative 4 divided by 4 is 1. And so we've moved that 4 out the front. And now we're left with this 9a, 10a squared minus 5a on the bottom. And we're again in this position where we're saying, what can we take out of top and bottom to then cancel? Now it's a bit hard to see, but we can actually take 2a minus 1 out of this. So if we kind of have a think about our box method, we know we've got to end up with 2a squared, 10a squared and we know we want to take out 2a minus 1. So 10a squared, or 2a times what equals 10a squared? I think it will probably be 5a. And then 5a times negative 1 is negative 5a. And so we see that what we've just got here is the same as what we've got here. And so we can replace this with 2a minus 1 and 5a. So we end up with 8 outside of 2a minus 1 on top of 9a times 5a times 2a minus 1. See, so we've replaced what was here with this. And from that point, we can say, oh, get out the cancelling colour again. We've only got multiplications, so we can cancel this term with this term. And we end up with 8 over 9a times 5a equals 8 over 45a squared. So that's our simplified version. So that's what we're doing there. That's looking at algebraic fractions again. Let's just have a recap over there. So we said the laws for numbers are the same as the laws for pronumerals. We wanted to simplify this equation. First we flipped it, top times top, bottom times bottom. Then we had a real think about what we're actually doing when we're cancelling fractions, and we found out we can take out a common factor. And that common factor was this 2a minus 1. We then cancelled the 2a minus 1s from the top and the bottom, and we ended up with 8 over 45a squared. Now we'll have a look at solving exponential equations. 4. Let's think of an example. Something like 16 to the power of x times 64 3x minus 2 equals 8 squared. And the key thing, one of the key things to notice here, I don't know how that keeps on happening. One of the key things to notice, one of the key things to remember when we're in this kind of position is what we're trying to do is to get bases the same. So what we're looking for is we're looking for a number that to the power of something equals 16, a number that to the power of something equals 64, and a number that to the power of something equals 8. And that number is 2. So 16 is 2 to the power of 4. We've replaced the 16 with 2 to the power of 4. We can replace 64 with 2 to the power, remember we had 6 earlier before, and we've still got this 3x minus 2. And then we've got 8 is replaced by 2 to the power of 3. And we've got it still squared there. So we've replaced 16 with 2 to the power of 4, replaced 64 with 2 to the power of 6, and replaced 8 with 2 to the power of 3. Now what do we do? Well, now we can think about our index laws again. And we've got this situation. A to the n, all to the power of m. So now what we can do is we can, sorry, I'm struggling with the computer today. Now we can say 2 to the 4, all to the power of x, is 2 to the power of 4x. 2 to the power of 6, all to the power of 3x minus 2, is 2 to the power of 6 times 3x, which is 18x, minus 6 times 2, which is minus 12. And this becomes 2 to the 3 times 2, which is 2 to the 6. Now we use another of our index laws, and that's for this multiplication, which is something 2 to the something times 2 to the something else. Coming up here, a to the something times a to the something else equals a to the n plus m. So you add the two powers when you're multiplying over a common base. Add the two powers when multiplying over a common base. So when we add 4x to 18x minus 12, we group like terms, or apples with apples and oranges with oranges, as I have said in the past. So we've got 2, 4x plus 18x is 22x minus 12 equals 2 to the power of 6. So we wanted to solve this equation. And solving this equation means work out what x is. And so now we've got this expression where we've got 2 to the power of something involving x and 2 to the power of something not involving x. And basically what we've got, if we've got 2 to the power of something equals 2 to the power of something else. And so it should be clear here that these two things better be the same. Because if these two things aren't the same, if they're not the same, for example, this was 2 and this was 3, then we'd have 2 to the power of 2, which is 4, and 2 to the power of 3. And 4 does not equal 8. Right? So these things better be the same. And the way of algebraic, or the way of mathematically writing these things are the same, is to write this thing is the same as this thing. And from there, it should be relatively clear to just add 12 to both sides. 22x equals 18. Divide both sides by 22. X equals 18 over 22. And divide, simplify. Take out the common factor of 2 in the 18 and the 22. So x equals 9 over 11. So that's how we do that one. We essentially want to get bases the same so that we can say that if we've got 2 to something and 2 to equals 2 to something else, those things better be the same. So we can go straight from this line to this line and then just use our normal algebraic techniques. So, hopefully that session was helpful, guys, just getting you familiar with indices.